So continuing on with our discussion on quantum mechanics, we have the quantum particle in a box. In the previous video, we covered Schrodinger's equation. In this video, we'll see how the Schrodinger's equation is applied to a particle confined in a or in what could be considered as a potential box. A particle confined to a region by two potential barriers. So the quantum particle in a box, consider a particle of mass m, and that particle is only allowed to move along the x direction or x-axis, and its motion is confined to a region from x is equal to 0 to x is equal to L by hard and rigid walls. So you have a wall here at x is equal to 0, and you have another wall here at x is equal to L, and our particles is confined in the region between the two walls. So, for example, you have a particle moving to the right, and then it encounters the wall, so it moves back until it encounters the other wall, and then it simply moves back and forth. The particle is confined to move on the x-axis between x is equal to 0 and x is equal to L. This physical situation is called the infinite square well and is described by the potential energy function U. For U at x is equal to 0 to x is equal to L, the particle is allowed to move freely along the x-axis, so U is equal to 0. On the other hand, at x is equal to 0 and beyond, so less than 0, at x is less than 0, U, the potential energy, U is at infinite value, meaning the particle must have an energy as great as U to be able to pass through to move along x less than 0. The same goes for x is equal to L. At x is equal to L, you have the wall. At x greater than L, the potential energy is also at the infinite value. U is equal to infinite, meaning to be able to pass through, the particle must have energy that's just as great as U. Since an actual particle cannot have infinite energy, the particle is confined to move in the region between x is equal to 0 and x is equal to L. So the particle will simply move back and forth from x is equal to 0 to x is equal to L and then back again. Since within this region x is equal to 0 to x is equal to L, within that region the particle is allowed to move freely, U is equal to 0, we have a free particle. And for a free particle, we can use the time-independent Schrodinger equation. U is equal to 0, that means U times psi, the term U times psi will be 0, leaving us with negative h bar over 2m is equal to double partial differentiation of small psi is equal to E times small psi. Furthermore, aside from being able to use the time-independent Schrodinger equation, if we simply limit our focus in the region between the two potential walls from x is equal to 0 to x is equal to L, the probability of finding the particle is of course 100% since the particle is confined in that region. So the probability P, integral from 0 to L of the square of the absolute value of small psi times dx is equal to 100%. At x is equal to 0, small psi is 0. At x is equal to L, small psi is also equal to 0. So these two equations basically describe our particle that's confined in a box. The quantum particle in a box. The solution to this, to the time-independent Schrodinger equation, is basically an oscillating wave function. Notice, you double differentiate with respect to x and still end up with psi. So you double differentiate small psi and still end up with psi. That means you have an oscillating function. You have, say, a sine function or a cosine function. For an oscillating wave function, the most general form is given by a cosine of kx plus b sine of kx. As mentioned, small psi is cyclical. It could be sine or it could be described by a cosine function. The general form is it's described by both cosine and sine. Now, if we apply our border condition, psi of 0 is 0 and psi of L is equal to 0. So let's set x to 0 for psi. So small psi of 0 is equal to a, x is 0, so cosine of 0 is just 1. But sine of 0 is 0. That means if psi of 0 is 0, a is equal to 0. Our equation for small psi therefore simply becomes small psi is equal to b sine of kx. We still have x is equal to L. Psi of L is equal to 0. So let's now apply this border condition. Psi of L is equal to b sine kl is equal to 0. That means sine kl is equal to 0, and that only happens when kl is equal to n pi, where n is equal to 1, 2, 3, 4, 5, and so on. So we have our equation for small psi. Small psi of x is just equal to b sine of kx. Replace k by n pi over L. So you have n sine of n pi x over L. So the only thing unknown for our small psi is b. If we use this equation of small psi into our time-independent Schrodinger equation and into our equation for probability, we end up with the following equation for energy. En is equal to n squared pi squared h bar squared over 2ml squared, and psi of nx is equal to psi n of x is equal to square root of 2 over L times sine of n pi x over L, where n again is equal to 1, 2, 3, 4, 5, 6, and so on. N is referred to as the energy quantum number or the principal quantum number. From these two equations, we see that the energy of a particle confined inside a box is quantized. The energy is simply limited to E1, E1, E2, E3, E4, and so on. We have the naming convention for the different so-called energy levels of our particle in a box. The, the lowest energy level, n is equal to 1, E1, is referred to as the ground state energy of the particle. E2 is the first excited state. E3 is the second excited state. E4 is the third excited state, and so on. The stationary states, psi of n, sine of n pi x over L, you have basically what is referred to as standing wave states. At n is equal to 1, you have psi 1. So basically just one segment and it's stationary at that. So it's as if you have a standing wave. As you go from N1 to N2, you now have two segments or a whole sine function. And then you have N3 and then N4. N is equal to 4, N is equal to 5, and so on. Again, psi, small psi is the wave function of our particle. And from the wave function, note we are able to calculate the probability of finding the particle. So depending on the quantum number, n, the probability of finding the particle at a particular region between 0 and L changes. Because the wave function psi basically changes as you go from one quantum number to the other. So you have your quantum particle in a box. So that's it for now. In the next video, we'll take a look at the examples part of our discussion on quantum mechanics. So thank you for watching.